Hi all. Apologize for missing class today. I'm going to go through a couple of concepts that we will review a bit more on Monday. We're going to be talking about different types of halogenated alkenes today and talking through a reaction called the NBS reaction. Alkanes. We've done a couple of reactions already to make halogenated alkanes, so we talked about these a little bit on the last exam. Starting from an alkene, we can throw in HBr. Let's just generate this bromo alkane here. Similarly, Br2, what's this, dibrominate. And then triple bonds will let us tetrabrominate. Other reactions that make haloalkanes. We talked about this one back in exam 2. This was our radical bromination and chlorinations. So taking something like this here, throwing in Br2 and light. Bromine is going to be highly selective for our more substitute position, which would be this tertiary position here. So this lets us brominate on this tertiary position. Chlorination's a little less selective. This one, you're gonna get a mixture of products. I'm not gonna go through all the math for it. If we do the math, these two secondary positions, this one here, and then this lower one here, end up being our two most likely and should end up leading to our major product because this thing has a big plane of symmetry down the middle of it. So, bit of review on these. Today we're going to talk about a reaction which adds things to what's referred to as an allylic position. In terms of alkenes here, this alkene there's different positions. There's what are referred to as vinylic positions and allylic position. So our vinylic positions, I write this in red. These are going to be directly attached to our double bond. So these three hydrogens here are considered vinylic hydrogens versus allylic hydrogens. Are going to be this one carbon away here. And if we had something more complicated, an extra bond here. All of these hydrogens being drawn in are considered allylic hydrogens. So those hydrogens all, when deprotonated, so let's take, we're to take off of this one here. Giving us a negative charge at this position. This has resonance to our double bond here. which is what makes these vinylic positions useful, because they're the positions that are going to lead to something that's resonance stabilized. All right, so let's talk a little bit about stability and double bond stability. So carbocation stability. We talked about this a long time ago. Methyl be our least favorable. Primary is less stable than secondary. Is less stable than tertiary here. And then after this, things with resonance become more stable than things without resonance. I'm not going to go too far into how much resonance. We're going to talk about that a little bit after we talk about double bonds. So this is our least stable. This is our most stable. This general trend follows any sort of high orbital system. So that was carbocations. You can also have carboanions. So negative charge, a negative on a primary center is less stable than a negative on a secondary, then on a tertiary, then on a center with resonance. This also works with radicals, which is what we're going to talk about today. So, primary radical, least stable, secondary radical, tertiary radical, radical with resonance. So, something we haven't really talked about is double bond stability. So, in terms of double bonds, your least stable double bond is going to be just ethene double bond by itself. As we start adding in substituents, it starts getting more stable. So we would call this it's a non-substituted. Be less stable than a mono-substituted alkene. We have one group coming off of our double bond. And then technically cis would be less stable than trans. Followed by, so these are di-substituted, followed by something that has three things coming off of it. And then lastly, double bond with four things coming off of it. So if we were to look at a couple of double bond systems, comparing these two double bonds, I'm going to redraw this one. This one got a little messed up. This double bond over here has 1, 2, 3 substituents. We don't count the hydrogens. This would be a tri-substituted. Versus this one has 1, 2, 2 hydrogens coming off of it. So we di-substituted. This one here would be more stable. So we're going to kind of merge concept of double bond stability, concept of radical stability here. And there's going to be points where our double bond stability is going to trump our radical stability. So let's take a look at this last part of our radical stability here. So let's say we have something like okay. Taking a look at this radical here, Doing resonance with radicals is very similar to other types of radical or other type of resonance. We're going to use our half arrows though. So we'll have a half arrow come from this radical in order to make our double bond, another single electron coming from our double bond. And then this electron here will get pushed to the top here. This is going to give us, so we formed a new double bond here. This electron got moved over to here. We did radical resonance here. So between these two structures here, if we were looking at them, you might say this one is a primary radical. This is a di-substituted double bond. Versus over here, this is a secondary radical. This is a mono-substituted double bond. Okay, so in terms of stability, our double bonds are going to trump our radicals when we're dealing with something that has resonance here. So di-substituted double bond compared to a mono-substituted double bond, this is going to end up being more stable. Even though we have a secondary radical versus a primary radical, this is the one we're going to care more about. So double bond trumps radical stability. All right. Why do we care about this? So we're about to learn a reaction that uses this concept in order to do brominations at our allylic position. So if we take a reagent called NBS, this is N-bromosuccinimide. You don't need to know the structure for this, but I'll draw it out once. It's got this Br. It's going to end up releasing a Br radical. Essentially, what's going to happen is what you'll have happen is you're going to form a radical at our allylic position. So for this example here, our allylic position is one of these two green hydrogens. And then we're going to have a bromine come together with this radical in order to form a product. So this would be one product where we would make the radical based off of this. The other possibility is that we're going to do resonance and see what it looks like. So for this here, a resonance structure, essentially we're going to swap the double bond and the radical, but I'll draw the arrows. So one electron goes to here, one electron goes to here, other electron ends up at our terminal position. This gives us our other radical, which we can then have form a different product. So looking at these two radicals, this is a mono-substituted double bond. This is a di-substituted double bond. I'm going to write as DB instead of double bond. So this is our more stable compound here. It's got the more stable double bond. it's going to lead to our major product. So let's do another one. So taking a look at this here, this is our double bond. Going one carbon away, we have 3 hydrogens, so only one option here. This has 1 hydrogen on it. If I pull the proton from it, we are going to compare this to the other resonance structure. So I can move this electron, shift here. This is going to give us our other resonance structure. Of these 2 resonance structures, this is a mono substitute, this is a tri substitute. This is our more stable one. Our product will end up where this bromine radical is. Or sorry, the bromine will end up where this radical is, giving us this product here. All right, let's do some ones where we have multiple substituents. Or sorry, multiple allylic positions. So for this one here, it's still going to be easiest to pull a hydrogen off of a tertiary versus a primary position. So looking at these 2, I've got 2 allylic positions now. This one on the left is more substituted than this one on the right, so we're more likely to form a radical on the right here. Sorry, on the left here. We've got a disubstitute double bond. Our other resonance structure. Nope, that's the same one. Will look like this. This has 2 substituents coming off our double bond. This one has 3. So this is more stable. That Br should form where the radical is in this product. All right, let's do a more complicated one. I'm going to get a new sheet of paper for this one. This one's going to be let's see. All right. We've got a lot of different positions here, a lot of different options. We're adding an MBS. There's 3 different allylic positions. I'm just going to draw one of the hydrogens for this one instead of all 3 of them. So this one's tertiary, primary. We're going to ignore the primary. We've got 2 tertiaries that can compete against each other. So at this point in time, we're going to have to draw multiple of these reaction coordinates. So starting with this one from this left proton, we could generate this radical. or this radical here. So let's start with this one. We are going to have another resonance structure. So if I shift this over, shift this over, shift this one to the end. Gives us a different resonance structure. Looking at these two, I've got a tri-substituted double bond, tertiary radical. Tri-substituted double bond, tertiary radical. Both of these are going to lead to product in an equal amount. We'll get a little down arrow. Let's draw a little line here. Okay. This other one here can do resonance. Shift our electron, put this one over to the other end. Should make our new radical here. Now we have a tri-substituted double bond versus a tetra-substituted double bond. So of these, this should lead to our major product. Okay, so this is where things get a little bit confusing. Because we have to think of these as kind of like one big set of reactions here. So all of this is happening when we start our reaction. 50% of it's going to go down this pathway. 50% of it's going to go down this pathway here. So we got two different radicals that are almost identical in terms of stability, which means in terms of product, we'll make 25%. So splitting that 50%, 25% over here, 25% over here. From our other pot, we had 50% here. This is going to mostly favor this one, which means it's going to keep its 50% into this product. So because of that, this will end up being our major product. I'm going to walk through that one more time. So you do this reaction, you got these two positions that are most allylic or most substituted. They both form radicals in an even mixture. On this top one, the two resonance structures of the radical are the same amount of stability, so they both can lead to a product. That'll split our 50% into a 25% pot and a 25% pot over here. On the other hand, for this one, this radical is more stable than this one. So this one's just going to go to product. It's going to take all this 50% and go to our major product here. So because we split this one again, we'd have 25, 25, 50% here. This is the majority of what's formed in our reaction. So this would be considered our major product. All right, so I'm going to stop here. On Monday, we're going to review this. We'll talk through a couple of these problems and then get started on some new material. So thank you guys. Hope you have a great weekend.